So today we are going to study about a deadlock. Now to study about deadlock, we are going to understand that what are resources and what are the instances of a particular resource and the various other things. Let us consider that our system has basically n different types of resources, that is R1, R2, R3, R4 up till n different types of resources, and each resource type Ri basically has Wi different instances. What are the instances of a particular resource type? They are basically the different copies of the same resource. For example, if I say that a tape drive is a resource, and if my system basically has 10 tape drives, so basically the number 10 are the instances of a particular resource type, which is tape drive. Now, what a process can basically do? It can basically request for a resource, it can basically use a resource, and it can basically release a resource. So it can request for a resource, it can use a resource, and it can then release that resource after it has satisfied its requirement. A set of process is basically in a deadlock state when every process in the set is waiting for an event that can be caused only by another process in the set. Let us understand this concept with an example. We are considering that there are three processes in our system, which is P1, P2 and P3, and there are three tape drives which are available. Let us denote the tape drive by some rectangular boxes. Now at a particular moment of time, P1 is using the first tape drive, which is marked as 1. P2 is using the second tape drive, which is marked as 2, and P3 is using the third tape drive, which is marked as 3. Now P1, for completing its to satisfy itself, it needs the tape drive 2, and P2, for satisfying its need, it requests for tape drive 3, and P3, for satisfying its request, it needs tape drive 1. So at this moment of time, the tape drive 1 has been allocated to P1, tape drive 2 has been allocated to P2, and tape drive 3 has been allocated to P3. But none will be able to release these tape drives because they have requested for another resource which is basically held by another. So if P2 will not release the tape drive 2, P1 can't get it. If P3 will not release tape drive 3, then P2 won't get it. And if P1 is not going to release tape drive 1, then P3 won't get it. So this is a scenario where we can say that deadlock occurs, because here all the three processes request for another tape drive. They arrive at a deadlock state waiting for a tape drive to be released by another process. So for an event to occur, that event is releasing a tape drive. For that event to occur, the processes are dependent on another process. And this is how we can get a deadlock scenario. Now, how we can basically characterize a deadlock scenario? The deadlock basically has the following four characteristics. Now we are going to study about the deadlock characteristics. In the deadlock characteristics, we are going to study about mutual exclusion, hold and wait, no preemption, and circular wait. So now we are going to know that what is mutual exclusion. Mutual exclusion is basically a phenomena where a resource instance can be held by one process only at a time. So if you are having 10 resource instances of a particular resource type, then each and every resource instance of that process can be occupied mutually and exclusively by only one process. So one resource instance can't be shared by multiple processes. Now we are going to know about what is a hold and wait scenario. In case of a hold and wait scenario, now we are going to write about hold and wait. Let me write it in this place. If a process is holding a particular resource instance, and if a particular process has requested for another resource instance, it will hold the instance which it is actually using, and it will wait for getting that instance which it has actually requested. So holding the instance allocated to it and waiting for the instance which the process has requested. So what I did basically say that when it has requested for a process, matlab for an instance of a particular resource type, and it is actually using another resource instance, so it will keep it and will wait for the instance it has requested. So in this case, when P1 had requested for the tape drive 2, so it will wait for getting tape drive 2 and it will hold this resource instance which is tape drive 1. So this is another characteristic which we can basically have in case of deadlock. Now, no preemption. When a process is holding a resource instance that instance cannot be snatched away from that process. So what is this? When a process is holding an instance of a particular resource type, that instance cannot be taken away from that process. So we can't snatch a resource instance from a particular process. If it is holding a resource instance, if it is using a particular resource, it will have to stay with it. When it completes its usage, then only the resource instance will be free. Otherwise, it will not be free. We can't snatch away. So we can't preempt the resource instance from a particular process. So this is another characteristic which we know about the deadlock. Now the last and the most important thing which we basically have is a circular wait scenario. Let us explain the circular wait scenario with n different number of processes. Suppose there are process P0, P1, P2 up till Pn minus 1, and there are different resource instances of a particular resource type. This instance is allocated to this process. This instance is allocated to this process. This instance is allocated to this process. The arrow which is pointing towards the process is basically an allocation arrow. That means this instance is allocated to this process. This instance is allocated to the nth process. Now we have got a scenario where P0 requests for this instance, P1 requests for this instance, P2 requests for the next instance. Then the Pn minus 2th process will request for this instance. Let us consider this is the Pn minus 2th process. Pn minus 2th process is requesting for this instance, and then the last or the nth process will basically request for this instance. So obviously by this diagram it's basically clear to us that it's almost a circular wait kind of scenario. P0 waiting for the this instance, P1 for this instance, and then the nth process is waiting for the instance which is held by the 0th process. So this is a circular wait scenario, and this basically results in a deadlock because everyone is waiting for an event to occur. What is the event? Everyone is waiting for an instance to get freed up which is held by another process, and every process is waiting for this scenario. So a scenario will not come where a particular instance will basically be released by a particular process. So this circular wait scenario will basically, or eventually we can rather say, will lead to a deadlock. Now before understanding this deadlock characteristics in details, let us study about the resource allocation graph. In resource allocation graph, normally in computer science or in mathematics, we have studied about graphs. So basically in a graph, there are basically two components. One is a vertex set, and one is the edge set. Now let us study about the resource allocation graph. Resource allocation graph. We can write it in an abbreviated format, which is RAG. Now obviously in this resource allocation graph, like any other normal graphs, we are going to have a vertex set and an edge set. The vertex set will be denoted by V, the edge set by E, and the graph will be a collection of the vertex set and the edge set. This is this everyone of we know. Now let us consider a particular term called P. Now what is this? What does this letter P stand for? It basically tells the set of all the processes in the system. So all the processes which are basically existing in our system, the set of all those processes is denoted by the letter E or the term P. Okay. Now what is denoted by the term R, capital R? It basically denotes the set of all the resource types present in the system. So R is basically the different resource types. For example, tape drive is a resource type, a hard disk can be a resource type, any IO device can be a resource type, for example a printer. Okay, so these are the various resource types which we can basically have. So R basically stands for the set of all these resource types present in our system. Now we're going to define that what is this vertex set V. The vertex set is basically the set of all processes union the set of all resource types. This is the representation of the vertex set. It's P union R. So the processes and the resource types will basically make the graph, the vertex set of the particular graph. And what is the edge set? It will be the request edge union the assignment edge. Now let us see this graph. We have seen that this instance has been allocated to this process. This is an assignment edge. Now this process is requesting for this instance. This is a request edge. So when we have a edge from process Pi to resource Rj, this is a request edge. And when we have a edge which is from the request Rj towards the process Pi, this is basically an assignment edge. So our graph, the edge set of our graph will contain the request edge union the assignment edge. Now we are going to study an example of our resource allocation graph. Let us see that this is the R1 resource type, this is the R2 resource type, this is the R3 resource type, and this is the R4 resource type. This is the process P1, this is the process P2, and this is the process P3. Now we are going to see some request edges and assignment edges. Okay. Now we are considering a request edge from P1 to the resource type R1. We are considering that each and every resource types are basically having only one instance. Let us denote the one instance by a dot. So each and every resource types are basically having one instance. Okay. Okay, let us consider the R3 resource type and the R4 resource type to have 2 and 3 instances respectively. Okay. Now P1 is requesting for the only instance of resource type R1, and that instance has been allocated to P2. Then P2 is requesting for this instance which has been allocated to P3 process. Now P3 is requesting for an instance of resource type R3. Now the first instance of this R3 resource type has been allocated to P1, and the second instance of this R3 resource type has been allocated to this process P2. So this is the entire scenario which I'm having. This is an example of RAG, or the resource allocation graph. So we can clearly see that it's a collection of the request edges and the assignment edges. This is a request edge and this is the assignment edge. This is a request edge and this is the assignment edge. Now we are going to see that if we are going to see some characteristics of this resource allocation graph. If the resource allocation graph RAG contains no cycle, then there is no deadlock. This is a very important concept that if by constructing the resource allocation graph, if you are having no sort of cycles in this particular resource allocation graph, then we are not going to have any sort of deadlock. If the resource allocation graph RAG contains a cycle, if there is only one instance, this is a very important concept, one instance per resource type, then there is a deadlock. So if for every resource types we are basically having only one instance, and considering this scenario, if our resource allocation graph basically contains a cycle, then there has to be a deadlock scenario. Okay, now if